is another way of looking at learning with learning control, right. So I am going to think about how can I learn control using a value iteration kind of an approach, right. So what do I want? So that is my target, right, and that is my current estimate of something, right. So remember I am learning the Q function. So what does the Q function tell me? Take an action, whatever is the action given in the Q arguments, right, and then behave optimally thereafter, right. The first action is whatever I take, right, there is no question of optimality or anything about it. That is be the thing that I am looking at, right. I should move away very quickly after writing something on the board there, otherwise Shubha will wave me away. Right, I mean people kind of buy that, right. So what I am really looking for when I say Q star I say is expected value of RT plus 1, which is what I get for performing A, plus gamma times V star of whatever comes afterwards, correct. But we know about V star, we can write V star in terms of the Q function. How is that? V star max, it is a best, right, there is no pi here, I am talking about optimal value function, right. So this is in turn equal to correct. Now we can now do our stochastic updating rule. This is my target, this is my current estimate. So putting this together I can just write a rule like this, right. So what will be my rule? So target minus current estimate, right. So people get that, right. I mean what we are trying to here, earlier we were just trying to take the definition of the Q function which is the expected value of the return. Now I am looking at the definition of the Q function as the expected optimal Q function as the expected value of this expression, right. Now I am converting that into an update rule, okay. Now I can put in the rest of it around this. So what is a nice thing here, just like in the expected SARSA, I do not have to pick the action beforehand, I can pick the action afterwards also, right, because I am only doing the max, right. So I do not have to do the pick an action first and then apply it, right. I can move this within the loop, right, remove this, right, I can flip this around basically.
Why is that so important, like selecting an action even before?
Why is it important?
Why is it like, why are you so concerned about looking after before updating?
Why am I so concerned? That is because,
It could come back to us.
yeah, so there are a couple of things, yeah. So one thing, the most straightforward answer is it could come back to S, in which case I would have changed the value function, right. I would have used one A for updating this here, assuming that is the A I am going to take, right, but then I would actually perform a different A, in which case my return, see what I was trying to do here was substitute my return, right. So I am going to say RT plus 1 plus gamma this, because that is that's a sample of the return, right. So if the sample of the return, that means I should actually be sampling it according to whatever updation I am making, but I will not be doing that, I will be sampling by a different action. If I pick another action after I do the updation, okay, so I will be breaking the assumption that this is a approximation for the return. So that is the reason we need to pick the action beforehand and then stick with it, right. And later on when we see how we will be using an approximate function, value function, right. We talked about contextual bandits, right, talked about policy parameterization, like that you can use a value function parameterization. When you use that, you do not have to come back to the same state, right, because of the functional form. If I change the value in one state, it may change it in some other state also. So the whole policy would get messed up, so it becomes a little tricky then. So we essentially the trajectory along which I am doing the updation will be somewhat a messed up version of the trajectory which I am actually taking, right. So it might lead to some trouble in convergence.
Even here, maybe we are not affecting 18 plus 1, but it does affect 18 plus 1.
Which one? Yeah, but that's the action I will actually be performing, right. So it is fine, as long as that is the action I am performing, it is okay. Your question is you keep changing the policy anyway, right. Yeah, that is why I said we do not use an explicit representation of the policy anywhere, so it is okay. So I really do not know what is the policy I am estimating the value function of, yes, just that as epsilon and alpha go to 0, it will converge to something at the end, right. As long as the return I am using here, when I actually roll it out, right, I can roll it out. When I roll out the return, when whatever I am using is using all the actions I took, then I am fine.
So in a way, is the policy encoded in the initial values of Q or something?
What's that?
How are we giving it a policy at all?
Yeah, we bring on the initial value of Q. That is the policy you start off with. Yeah. So you could actually make it a valid policy, or you could start off with all zeros, in which case it is a uniform random policy. It will just pick all actions with equal probability to begin with, right. So you can do the same thing here. It's just empty space, okay.
When you say pick 80 plus 1, I don't necessarily have to execute it, right? I can pick it in simulation.
You don't have to execute it, you just pick it. The execution happens after you have done the updation.
Okay, then what is the distinction?
I am picking it according to QST before I make the update. Here I am picking it according to QST after I make the update. QST plus 1, okay. here when I say pick an action for QST plus 1, that is before this updation is happening. So if I use Q old, Q new, you will see that here I am using Q old, here I am using Q new for picking the action AT plus 1. I also put that thing in bracket, I will come to that, why I put that pick action AT according to QST, I put that in bracket. But you can see the difference between this algorithm and that algorithm, right, nothing much except for that simple change in the update rule. If you cool alpha and epsilon properly, it actually converges to the optimal policy. Okay, what will the second algorithm converge to? Optimal policy. Okay, provided you cool the alpha properly, you have to decrease the alpha properly, it will converge to the optimal policy. And this one, if you have to decrease both alpha and epsilon properly, it will eventually converge to the optimal policy.
How do you put it? I mean, is there some formula which say you should pull it by this way?
Yeah, for alpha you have the usual stochastic averaging formula, right? So, yeah, tell me. Huh? 1 by T is one thing that will fit the conditions, right? So, summation alpha should be infinity, summation alpha squared should be less than infinity, right? So, that is basically the conditions for alpha. So, as sum over all alphas, so essentially you have to put an alpha T there and sum over all alpha T. So, just summing over alpha T should be infinity, summing over alpha T squared should be bounded less than infinity. So, that is essentially the condition. So, because the alpha T equal infinity tells you that you are making enough updates, and the alpha T squared goes to, converges to a point less than infinity, means that you will eventually stop making updates. Okay.
Why bother using the first method at all?
Right?
Why bother using the first method at all when you can do the second one?
Good, that is what the rest of the class is all about. So this algorithm on the right is probably the most popular reinforcement learning algorithm people use. I said when I wrote down SARSA, I said this is the second most popular, right, and that is the first most popular, and it is called Q learning. So chronologically TD0 came first. I think Rich proposed it in like 84. Yeah, I think Rich proposed TD0 in 84 and showed convergence in 88 or something. And Q learning was proposed by Chris Watkins in 89, and SARSA was proposed by Ramari Niranjan maybe 91, 92, I do not remember the exact date, sometime around that. So surprisingly both Watkins and Ramari Niranjan are from England. So a lot of the early algorithms for RL came from England. Anyway, so Q learning is amazing. So what is even more amazing about Q learning is that since I do not care what is the sequence on which you are picking the actions, right, here I am using an approximation to the optimal return, right, I am not looking at the current return, I am looking at an approximation to the optimal return. So I do not care about the trajectory. In fact, in Q learning I do not even have to sample according to any trajectory. In fact, the next action I execute need not even come from ST plus 1. I can arbitrarily reset, if I have a simulation model, right, I can arbitrarily reset to some other state, right, and then sample one action from there, update Q learning, and then go and take an action from somewhere else, some other state, update using Q learning. I can just do a proper asynchronous generalized policy iteration kind of an approach. I just sample from all over the place, just take one step each and keep updating it. But still it is better to update it along trajectories, like we saw in the argument for RTDP, right. If you update it along trajectories, it is more meaningful because the values would have more likely to have changed along those trajectories, right. So that is essentially why we sample according to the trajectories. So this thing need not be an epsilon greedy sample at all, right. So I can sample actions arbitrarily. I can just pick an action AT in ST randomly. Okay, doesn't have to follow any rule. So what does this do? It just tells me which action I am going to update next. Right? If I am not sampling according to trajectories, it will only tell me which action I am going to update next. So why do you want to pick according to this? So that you can, just like in RTDP, so that you can focus the updates along the most likely paths. So the reason you do it epsilon greedy fashion is that you quickly want to converge to the most likely path that you are going to take under optimal policy, and you want to do the updates along that most likely path. Okay, and that is why you use the epsilon greedy sampling for Q learning. Okay. So what are the advantages of SARSA? SARSA you can continue to explore, right, and while exploring you learn something that is taking into account the exploration. So what does Q learning do? That is why I am saying you can behave arbitrarily with Q learning, but if you choose to behave according to the Q function you are learning, here it does not take into account the fact that you are doing exploration. Okay. So why would that matter? So here is a simple grid world problem called the cliff world. So those squares marked in red represent a cliff. So if the agent wanders over the cliff, he is going to get a reward of -100, and to top it off, the agent will also die. Okay. Basically the episode will end, the agent will get a reward of -100 and it goes back to the beginning. Right, you start all over again, you reincarnate and you start going all over again, and otherwise you get a reward of -1 for every time step that you move. Okay. So everything is deterministic, so for every time step that you move you will get a reward of -1. Okay. And you have to try to get from the start to the goal as quickly as possible. No gamma here, gamma is 1, right. Whenever I say no gamma, it does not mean gamma is 0, it means gamma is 1. Okay. And so what do you think will happen? And while learning I use a epsilon greedy action selection. Epsilon, let us say I fix it at 0.1, I am not going to reduce epsilon, I will fix epsilon at 0.1. Okay. So what do you think is the policy? What do you think Q learning will do? What do you think SARSA will do? Well, we said both will learn optimal policies, and what is optimal policy here? Right, so here you go up, here you go left, right, right. So this is the optimal policy. Of course, if I want to write down the optimal policy elsewhere, maybe I can just write down arrows everywhere. It does not matter, right. So I can do down arrows everywhere or right everywhere except the last column where I go down. Right. This is optimal policy. There is no question about it. This is the optimal policy, right? At least for these states. Right. For these states you have a choice. You can either go right or down. For these states, this is the optimal policy, right? Okay. Will Q learning find this optimal policy? Yes. Will SARSA find this optimal policy? In this case it won't, because I have fixed epsilon at 0.1, right. So what will SARSA learn?
safest path.
You go up 2 steps.
Will this show up?
Depending on epsilon.
Epsilon I set at 0.1, let's say. Huh?
Depending on epsilon, it will take a safer and safer.
Yeah, it may take a safer and safer road. If I give you more rows, right, it will probably go. But then this is too small, right? It basically needs 2 exploratory moves to fall off the cliff, and I given it like 10 moves in which to take those 2 exploratory moves. So it's very high probability it will take those 2 exploratory moves, right? So it will try to stay as far away. If it just goes here, right, it will be just 2 moves, right? Now this is 3 moves. So that's the reason it will try to go as far away as possible, because the reward is sufficiently negative. I said minus 100, right? So that's a really bad negative reward. So it will try to go farther and farther away. So this is the difference between SARSA and Q learning, right? So SARSA takes into account the fact that you are doing the exploration, right? While Q learning might learn the optimal policy, right? It might also end up killing you more often while learning the optimal policy, right? There are also more naive answers for this, because if you continue to explore, right, not exactly naive but slightly less compelling reasons, if you are going to continue to explore after you finish learning, right, it is better to learn the policy through SARSA than through Q learning, because Q learning assumes that eventually you are going to be executing the optimal policy, right. But that is a reason for us not to execute the optimal policy greedily ever. Why? Huh? More better than stochasticity. What? There is a reason for us not to use the optimal policy greedily even after sufficient learning. Non-stationary. It is not the stochasticity I am worried about, it is the non-stationarity I am worried about, right. So if you are convinced that the world is not changing, then great, you can start behaving greedily after some time. But there is a chance if the world might actually, some things might happen, right, or suppose you are a robot learning in a world, right. So it is possible that obstacles can be moved around, right. So you do not want to become so rigid that you are completely unadaptable when things change, right. So that's ruinous. So you want to keep the option of being able to explore and discover new things. So you do not want to turn off your epsilon ever, right. In such cases it is better to use SARSA than Q learning, because Q learning kind of ignores exploration at all, right, and it converges to an optimal policy and then it sticks there, right. Right, and so the problem with the converging to optimal policy and sticking there is this, right. If I want to keep my epsilon on, then I will keep falling off the cliff. By every one single move I make, wrong exploratory move I make, I will keep falling off the cliff. So the expected reward I get for executing this optimal policy will be far lesser than what my agent believes it should be getting, because agent is ignoring the exploration. Okay, so that is the crucial difference between Q learning and SARSA. That is why you would like to use SARSA in many cases.
If the state space is very large, then also Q learning is good.
Huh?
There is no danger in this.
Q learning is actually good in some aspects. Huh?
It's not exploring, and the state space is very large.
Yeah.
And there is no danger.
Mm.
Then Q learning is good than SARSA.
There is no danger and the state space is very large. So why should the size of the state space matter?
Exploration. It's not doing exploring. Q learning is not exploring.
It's exploring. Why? I mean, Q learning can explore much more than SARSA, right? Because it ignores exploratory policy completely. You can actually have your agent behave completely randomly and still learn the optimal policy in Q learning. In fact, that makes Q learning a off policy method. right. You can do arbitrary exploration and still learn the optimal policy, right. So so the estimation policy for me is the optimal policy, and the behavior policy can be something completely random. So that is one reason you would want to use Q-learning in a large state space, because I can behave arbitrarily so that I get to explore a larger fraction of the state space.
But in the large state space, won't Q-learning be slower
Everything will be slow.
compared to Sarsa?
Both will be slow. Why would you think Q-learning will be slower compared to Sarsa?
We said that we want to quickly converge the optimal bar, and that's why we do epsilon greedy, and Sarsa will take account the exploration.
So I'm not 100% sure about the convergence rates between epsilon greedy, Q-learning and Sarsa. I'm not sure about the convergence rates. I do believe that Q-learning converges faster than Sarsa in general, and I'm not sure about large state space issues, but I'll have to look it up. Yeah, but you should know that these are the basic algorithms, right? If you want to operate in large state spaces, you will be using something else over on top of this. This shouldn't be using plain vanilla Q-learning and Sarsa and large state spaces. So there are other issues that will come into play, but I am not 100% sure about the comparison of rates of convergence between Q-learning and Sarsa. Right? Great. So any other questions on these two? Okay. So I have these three actually. We talked about expected Sarsa as well, right? And in fact, you can think of all kinds of hybrid algorithms, right? So for example, you can think of an algorithm that will take 1 step, 2 steps according to the current policy, and then use a max. Right. So what do I mean by that? It is something like this. Right. So this part is on policy, right. So that part is off policy, right. So that's why I said it's a hybrid kind of thing. So you can do all kinds of different kinds of samplers for your value function. Okay. So in fact, it's more common to use the Q function there. So that's still on policy, everything is on policy, but I am using more of the actual samples and less of the bootstrapping, right. Why I say less of the bootstrapping? Because it is discounted by a larger power of gamma. So the total contribution of the bootstrap thing will be coming down. Okay. So I can do all kinds of modifications to the return. So in fact, there was a time when we were trying to get a reinforcement learning agent to play what is the thing called, air hockey, right. So somebody in CFI wanted to do a project where he wanted to get an RL agent to play air hockey. In fact, he was building a physical system that was going to move the slider around, and he wanted to use RL to control it, and then it turned out in the simulator at least that he had built using a 3-step return like RT plus 1, RT plus 2, RT plus 3, then the Q function of the rest, that turned out to give a better performance for whatever reason, right. So it's kind of tied to the stochasticity in the system and how far ahead is the system predictable and so on and so forth. So I think it turned out that for at least 3 steps into the future the system was more or less predictable, and therefore he could use this kind of return. So it's very complicated things, right? It's not easy to figure out what is the right look ahead that you should be using for these returns. Okay. So they are more or less done with chapter 6.